but yeah, so this week, I'm not sure I don't think we talked about this too much in depth yet, but one also interesting topic about smart contracts is their deployment. So the fact that there's different ways to deploy contracts, and for different reasons. So at the core, when smart contracts are deployed, they're all deployed from an EOA, right? So from a wallet that is controlled by a private key, and you sign a transaction that creates a contract. And this is the way that contract is created is very similar to the create opcode itself. So basically, the address of the contract is independent of anything you deploy, but it's just based off of the nonce of your account and the address of your account. And that's used to determine the new address for the contract. And it's deterministic in the sense. So if you're deploying multiple contracts after each other, you can know that the fourth contract I deploy from now, it'll have exactly this address on the chain, or the sixth contract I have from now will have exactly this address. And this is super useful because oftentimes your contracts will have circular dependencies, right? So circular dependencies in the sense that you may have one contract that wants to call the other contract, and the other contract that might want to call back into this one. And but at the same time, you have to deploy them in a certain order, right? So somehow each contract needs to know about the other one. So let's check this out. Let me do my entire screen over here. All right.
Yeah, but you could create like setters to set the address you need after the deployment.
Exactly. So let's talk about that. Because yeah, the naive way, as you just mentioned, is to have a setter, right? So let's say we have circular. Let's call this file circular1, right? And in this file, we're just going to have two contracts, right? So we have our contract A, right, which is going to be dependent on contract B. So we can have here, we can have address internal B, and then we just have, and then maybe we have some owner, right? So we can have some owner, and then we can say, okay, in the constructor, what we will do is we will set the owner, right? So we'll just say owner. We won't do the whole thing with events and everything, just to make it simple. And then you can do, your function to set B. You have an address B, or depending on your naming convention, I'll put the underscore afterwards for this one, and then you can set B, and then very simply, you also need to check that the message sender is your owner. Okay, very cool. And then similarly, you can have a contract B that needs the address A for some reason, and then you can have set A, and then you can easily deploy them, right? You can deploy them in whatever order, and then the cool thing is here is that regardless of what order you deploy in, it's very easy to like set the dependency, right? You can just set, after they're both deployed, you can call set A on B and then set B on A, and it doesn't really matter. But this is not ideal, right? This approach is not ideal because why? Because now, whenever you want to use A or B in your contract, like in most cases, this won't even ever have to change, right? So for safety reasons, you may even have, you may even require that A is still address 0, right? So that it can only be set once. Because in many cases, when you have like, you're building up like a multi-contract system, you just want to connect them once at the beginning, and then you want to leave them in place. So often you'll just have even a requirement that they're not already initialized, right? So like this, I check, okay, it has to be empty default address, and then I can set it once. And also I can check that B is not equal to address 0. So just like a very basic check why it would be one time. And it's like a very common thing in contracts. So you have two contracts that are somehow interdependent. Like, for example, you have some sort of DeFi contract and you have your custom token, or you have some sort of central like collateral management system, and you have the different you have like different lending pools, or there's a bunch of like designs or structures where you might need multiple contracts. Now, this is quite inefficient actually, because now A and B, they're stored in storage. So every single time, so let's say I need A for some reason, right? So I have my interface IA that has some functionality, get value, right? And I have external view returns something, like, sure, it's not implemented, but here, and then I have some function, right, that I imagine that, does IA on A, and then needs to get the value for some reason. So the reason this is not very good and inefficient is because it's in storage. And again, storage is expensive, right? Even if you're only reading from it, every single time you read this A value, it'll cost 2,100 gas. And obviously this will add up very quickly. And you actually don't need this because, as you see, we're setting A and B. We're only setting them once. So what if we can somehow use constants, or at least immutables, to make sure that it's much cheaper to retrieve A? But the problem is, again, we have the circular dependency, right? So if we deploy A first, then sure, when we deploy B, we can give it the address of A, but A doesn't know the address of B yet because it hasn't been created, right? So how do we get around this? Well, the way we get around this is through your deployment procedure. So as mentioned before, if an
sorry to
EOA
interrupt.
creates...
Sorry to interrupt. Like Create2 will address this problem as well, right?
Yeah, exactly. So there's different ways to create deterministic deployments. And in fact, if you think about it, in EVM, all deployments have to be deterministic to some extent because the different nodes have to have consensus around what address this new code is going to be deployed to, right? It can't just be like a .random function because all nodes need to agree, okay, where's this address coming from? So for EOAs, normal wallets, the way the address gets created is there's some derivation functions, basically a hash, but you can imagine it's some function that does a hash of like something plus the address of the deployer. So you have the deployer address plus the nonce of the deployer, and that gives you the new contract address, right? And if you think about this, you can actually predict this in advance, right? Because you can see your address, right? You know what wallet you have or don't have that will deploy your contract. And then the nonce, well, you can know what nonce you have. You can check it on chain, and then you can see, okay, if my deployment procedure has this many steps and all these transactions are executed for my main account, I know that when I deploy A, it'll have this address, and when I deploy B, it'll have this address. So already when you deploy A, you can already know the address of B, even if it's deployed afterwards. Right? So I can demo this in a second, but basically how your contract would now look is, instead of having the setter function, you would just basically define it as an immutable, or even a constant if you want, but let's just do it immutable for now. And then here in your function, then you might not even need an owner, right, for the setter function. You just literally have B underscore, you set B once, and then you're happy, right? And then similarly here, you have your immutable A, and then you set A. And this is already extremely attractive because, one, your code is already simpler. Like look at all the clutter we removed. We don't have an owner anymore. We don't have setter. We don't have to worry about being able to reinitialize variables, or that we forgot an access control modifier and that somebody else can just like set the variable. It's like set once, and it's efficient to retrieve, right? Because now this literally gets converted to a push opcode in your final code. So instead of 2,100 gas, every time you need to use A, it's only 2,100 gas. But how does this look like when you actually want to use this? So let's write a test that actually deploys this, and let's actually make it public so that we can actually check it in our test. So let's make a test of circular one. So we just define our test here. Oh. Circular test, and let's import A and B from our source circular one, I think it was called. Right, so let's do test deploy. Let's create the deployer, because I think it'll change the address. So let's do deployer is equal to, we'll make a new address. We'll call it deployer one. So this will just create a new address and label it automatically. This is like a shorthand in Foundry. And then we can just do new A, right? And let's see what this looks like. So let's do forge test with 4 Vs. So 3 Vs will show you traces when the test fails, and 4 Vs will always show you traces. Oh, owner, did we forget to save? Oh, here, I forgot to reset this. All right, and Oh yeah, we need an actual address. So we don't know the address of B yet here. So let's just do NP address for now, just to see. And I think Foundry will also respect the create essentially. So here is 0x56, and if we do cast compute address, and then we take our deployer address here, and we do nonce 0, it should be. Maybe Foundry doesn't fully respect the. Yeah, okay, so we might have to write a quick script. Okay, let's write an actual deployment script. So we'll do circular.s. So now the differences here is that a test is actually ran as like a transaction in like a semi-virtual environment. And when you have like a deployment script, you can actually test it again in like a more real scenario. So I can have my script, and I can import script from forge-std script.sol, and let me start Anvil in the background. So Anvil is just like a local node. So basically, this is like a mini blockchain that I can run, and I just got a private key from Anvil, so I'm just going to store it in my environment variables. So this is important because if you have a real private key here and you accidentally commit it to your repository, you can lose money. In fact, actually, me and a friend, we lost money. We lost the hackathon prize because one of the people I was building with in the hackathon, they were like doing some tests locally, and then they put in their command line tool, they put their full private key, but it was local, right? But they accidentally pushed like a copy of their commands that they ran into a file and accidentally committed that, and then instantly some bot on the internet scraped that key, and the moment we received our hackathon prize a few weeks later, it instantly got withdrawn and stolen, basically. So be very careful with your private keys, and make sure that if you have a GitHub repo, that your .env is always in the gitignore file, so that, you know, if you imagine this is I want to commit something now, you see that the gitignore has .env, and env is not in here, right? So that's very, very important to note. But yeah, going back to our script, let's do circular deploy, and let's do we need to import AB from source circular1, and then Foundry scripts are defined by the run function, and then you can do start broadcast will actually send out real transactions for things you do in here. So if we do start broadcast, and then we want our private key, it's like for the person deploying it, so we can get it with VM.enviewent, we'll get a private key, and then we also want to at the end stop our broadcast, and then in here we can deploy a contract and see the address. All right, clear so far? Is everybody still following?
Yeah.
Oh?
You need to start broadcast. Oh yeah,
yeah. So basically, what start broadcast does is in Foundry scripts is that like all transactions you do here, including contract deployments, will actually trigger like a real transaction. So you can like automate your deployments with this. You can define it here, and I think this is actually an extremely good practice. You don't have to use Foundry, although I recommend Foundry, but to always have predefined deployment scripts and procedures, and then when you have your application audited, have the deployment scripts be part of your audit, because very often developers will just get their main code and logic audited and then think, oh, great, my contract works fine. There's no critical vulnerabilities. I fixed a few things they found. It's great. But oftentimes there are issues in your audit, depending on how good your auditors are, that may only be flagged as informational or low because they regard to like human error, right? That you may make during deployment. And when you review these issues, you're like, obviously, okay, this is like human error. This is fine. This is not going to happen. But you may actually make a mistake when you deploy. And for example, even Aave, that had, they spent literally millions on audits and formal verification and super fancy security procedures to make sure all their code was right. But at the end, I'm not sure if they got paid a bug bounty or if this was just like an internal find, but somebody found a critical vulnerability in Aave that was not related to the logic, but it was just related to the configuration deployment, because they did everything right. They audited, they spent millions on security, but they didn't have a great deployment procedure. So at the end, they had something misconfigured in production that would have allowed somebody to steal a ton of money because something was misconfigured. And obviously, this doesn't pop up in the audit, right? Because, okay, it's to do with human error and how you deploy things. So that's why it's I'd strongly recommend that you have like scripts that like predefine how you deploy things, because like this, auditors can check them too and see, okay, hey, actually this is wrong. And if you run the script like this, it'll actually lead to your contract being vulnerable or deployed in a vulnerable state. So yeah, just a word of advice there. But let's actually run the script here. Our RPC URL will now be our local host. So I'll just do localhost 8545 is the default thing. And if you run a forward script like this, it won't actually run it against the node. It'll just simulate it. And if you actually want it to send out real transactions, you can do minus broadcast. But let's first simulate it, and I'll add some V's so we can actually see the trace. So VM is not defined. Oh yeah, I forgot to say is script. So like this will inherit VM and all the different cheat codes. So traces. Let's actually get the. Private key here, or let's call it PK, because then we can also get our deployment address PK, and let's like forge std console to like this, and then we can actually log our address. So we can say the deployer is equal to some $s, and this will be our dependency. So let's do that. Console, oh, like this. All right. PK. Oh, yeah. Got to define it as an actual variable. Let's fix that. Ran successfully. Okay. So we have in our logs, we have our deployer address, right, which should be the first key. Which here the deployed contract address here. So a cast is again a part of Foundry and it has a bunch of different utils. So one is called compute address, which allows you to deterministically calculate addresses in advance. So if we take our deployer address, right, and then we say nonce 0 because it's their first transaction, we'll see 0x5b.
Sorry, I can't see the screen.
You can't see the screen?
Yeah, now I can. Okay.
Yeah, it's lagging.
All right. So yeah. So you have this address. It's lagging. Can you tell?
Yeah, but now I think it's better.
Okay. But the main point I want to demonstrate here is that this address that we deployed at can be known in advance, and we can actually compute it based off of the deployer. So now we can leverage this to, for our original point, create basically these two circular contracts. So let's do it in practice here. Let's write a deployment script that'll configure A and B to point at each other. So to help us with this, let's install Solidity. So Solidity is like a very useful Solidity library that has a bunch of different utils. And one of them that we'll be using now is called librlp. So librlp stands for library RLP, which is the encoding format of Ethereum, at least the current one. They're going to change it soon. But RLP stands for recursive length prefix. So it's just basically how you change like structured data. So maybe you have like an object of address nonce, and you want to encode it into like a byte stream, right? So this is just like a standard way of doing that. And then if we import this here, librlp has a function that lets us compute these addresses in advance. So let's librlp. So look, compute address, and similar to our command line util, it takes deployer, nonce, and then fully in Solidity, it does the hashing on whatever, and it gives you the address. So let's do that. So first we need our nonce, right? So let's get the nonce. We're doing vm.get nonce of our deployer. this is the nonce of the next transaction. And then we can say, okay, that the address of A is going to be librlp.compute address of the deployer, dep, and the current nonce, right? And then B, we're going to deploy right after, right? So every time you make a transaction, it'll increase your nonce. So that's why here we do +1, and then we have the address of B. And now we can very simply connect these two. So now we have
Is it lagging for you guys
that's
as well?
connected to
I
B.
can see.
Yeah.
Using this library, we can, in our Foundry script, calculate the address of A in advance, although we don't need to in this case, and then also B in advance, which we do need because B is not deployed yet. So we want to essentially predict where it will be. And then if we simulate this now, simulate the script. The library is not configured yet. Let me set up a remapping. So sometimes you have the library installed, but Foundry won't recognize it. So you just have to say that when I say Solady, I actually mean under library, Solady, and specifically in the source folder. And then it'll recognize it. And then now if you look, wait, let's actually get the addresses of these two to prove that we did it correctly. So let's do console.log. Let's do A, B, B. Okay. Let's do predicted A, predicted B. And then let's get the actual address. So we have address of A is equal to address of A. And then similar to B. So we can see what the real addresses is they got deployed to. And then we can get what addresses we
Where is console
predicted.
2, by the way?
Where is what?
Console 2. You import console 2 on line 21.
Yeah, exactly. Yeah, but I rename it to console just because.
What's the difference between the usual one and console?
So I'm not 100% sure, but I think console, like without 2, so console 1 basically, in Foundry is like the fully backwards compatible version with Hardhat. And then console 2 is actually not fully backwards compatible with Hardhat because it fixes a few bugs that Hardhat had and like a few formatting issues, I think. So it's basically the same functions, but slightly better, which is why I always use it, but not entirely sure, to be fair. I think you'd have to read the docs.
No problem.
But yeah, and then we check out our predicted address. So predicted A, and then we can do that, and then predicted B, and it should be the same. Okay, let's run this in a simulated fashion. And then we see that address of A is the same as what we predicted, and address of B is the same as what we predicted. So as you see, this allowed us to set up basically the circular dependency of these two contracts that depend on each other, and also saving us a ton of gas in practice, and also making our deployment procedure more secure. So this has a ton of advantages. Our code is simpler. It's more efficient now whenever you want to use A or B. And also you can make less mistakes, right? Because you're setting B once, A once, and that's it. You can never change it. It's by definition in the source code immutable. So that's one way of doing deterministic deployments. So another one that is also very interesting is create 2 based deployments. So as previously alluded to, deploying directly from your wallet is similar to when a contract deploys another contract with create. So similarly there, if you use the create opcode, or what happens if you like simply deploy a contract within another contract, is it'll use the create opcode, which will also look at the nonce of the contract, because contracts, they also have nonces, but they're only incremented when you actually deploy contracts, and it'll deploy something new. But an issue with this, if you imagine it from your own wallet, is that what if you make transactions in between, right? What if you mess up and I have some transactions here in between, like I need to send somebody Ethereum, or my deployment procedure has more steps. It can be harder. It can be, more error prone. to see exactly at what step are you going to have a certain nonce. And another one is you might want a vanity address. So if you look at, for example, Seaport, it has these cool addresses where they specifically mine them to have a bunch of leading zeros. Now, the reason, one, is this is kind of cool, but two, it actually saves gas, right? So if a contract sets an address with a bunch of leading zeros as a constant, the final bytecode will be smaller because it can use a smaller push up code. So instead of push 20 to push all 20 bytes, it can now use like push 13 because the first 7 bytes are just zeros. And also when you call a contract with a parameter being this address, you'll also save in call data costs, right? Because every 0 byte in call data costs 4 gas versus non-zero bytes, which cost 16 gas. So this is why these addresses are cool. And you can basically, the way these are found is you have a special piece of software, which is called like a salt miner, that'll basically find you a random wallet that when you deploy a contract at a certain nonce, it'll have always this address. But now, one complication of this is, as mentioned, what if you do transactions in between? And also, you may want to have the same address, like if you're deploying the contract on many chains, ideally you want the same address on all chains, right? Because it helps users prevent mistakes and also developers by just saying, okay, you don't have to worry about, okay, on this chain is this address, on this chain is this other address. Everywhere it's the same. There's just one global address, and you don't have to worry about it. And this is kind of harder if you're deploying from a wallet, because the wallet can get lost, it can get compromised, and because the address, when you're deploying from a wallet, if you remember, it does not depend on the code that you're deploying. It depends just, you can deploy whatever. So if you, for example, have a special key, like a special wallet that generates this nice address the first time you deploy the contract, right, at non-zero. So you imagine I mine some wallets, you can do cat's wallet new, and then eventually it'll find you, you just like check, the software is checking a bunch of wallets until you find one which has this magic address. So, but imagine it gets compromised, right? And then on a new chain, an attacker can deploy a contract from your wallet that will have this special address, but can have completely different bytecode. And then if people are relying on this address and like trusting it, that can be a big issue. So the way you solve this is through so-called create two factories. So create two is an EVM opcode that allows contracts to deploy new contracts. And the major difference with create two between create is that now the final address of the deployed contract does not depend on the nonce. It depends on the actual bytecode plus a salt. So you can imagine the salt is like a nonce, but you can choose the nonce. So it can be same every time. And if you change the salt, you'll also change the final address. But if you look at how the address is determined down here, it's the hash of the creator's address, the salt, and the actual code. So like the hash of the deployment, of the deploy code. And why this is really cool is now you can, similarly to a wallet deployment, you can, number one, you can predict it in advance. So you can have circular dependencies very cheaply. But two, you have the advantage that it's not dependent on nonce. So regardless when you deploy it, who deploys it, it can only have a certain address if it has that specific code and nothing else. And this is also what OpenSea uses, because now no matter on what chain you deploy, your contract to, it will only have this address if it was deployed without bytecode. There's no other way of having this address. And this is super awesome. So you have the leading zeros, you can have circular deployments, and you have full guarantees that you don't have to worry about your key getting compromised. In fact, all the parameters can be public, like the bytecode can be public, the salt, and then you can deploy it. And this create two factory that OpenSea uses here, called the immutable create two factory, it's available on a bunch of chains. Like if you look at like for example, BSC scan, it's also there. If you look at, other chains, like if you look at testnets, for example, if you look at Optimist, or you should look at, let's look at Optimism, for example. It also has this factory. if you look at the Sepolia testnet, is it still live? I'm not sure. I think they shut down Gurley, not Sepolia. Yeah, so also in Sepolia, you have the same. So you can use this factory across, I think they deployed it over like 50 different chains. So this is kind of the best way to, in many cases, it's the best way to deploy contracts, because also users, again, the big advantage here, on top of the advantages you get with other deterministic deployment methods, is here you have guarantee that the code was deployed in a certain way. There's a specific code that has to live with the address. And that's the main thing. And also, I think it's also faster to find like vanity addresses, you call these, when you have a certain thing that starts at the beginning, because the hash of the address is just determined by a single hashing step. So if you look at here, it's just a hash of address, which you can know in advance, salt, which is basically the thing you're varying, and also a fixed hash of your code. Versus with normal deployments, remember librlp, it's basically the hash of an address and a nonce. So if you're imagining you're generating a bunch of random wallets, every time you need to generate a new wallet to check if you found your magic address, you need to create a new set of public-private key. You need to derive the address, and by the way, the address is a hash of a public key. That means that if you want to find a vanity address based on an EOA or create one deployment, you need to do 2 hashes for every single step, versus here you only need to do 1 hash. So generally also, I'm not sure if this is benchmarked, but usually these software to find these vanity addresses are faster than the other one, because there's just less operations you have to do every step to brute force and find your magic address. I know I went over a lot, kind of rambling as well. So any questions up to this point?
So create2 creates address based on the code, but what about create1? So it didn't?
Yeah, so create1, the address, okay, it's not even documented here, but the address only depends on, actually, no, it is, okay. The address only depends on the creator address and the nonce, which means that if you imagine on 2 different chains, or even on the same chain, if a contract was created with create1, you don't necessarily know what bytecode lives at that address. You have no guarantees about that, because you can deploy any code, and because it has the same nonce, it'll have the same address. So even on 2 chains, you can have one type of code, like perfectly functioning DEX on the one chain on the address, and on another chain you may have a malicious contract that steals any money you put into it, because this doesn't tie the address to the code, if that makes sense.
Yeah, but the nonce is always different, because it's order of the transaction, so it's always different. So it will be always different address.
Yeah, it'll always be a different address with create1. But if you imagine on 2 chains, on 2 different chains, I can have the same address, right? And have 2 different contracts. Versus here with create2, you know that on 2 different chains, they'll only have the same address if they have the same code.
Okay.
I have a question about that create2 factory. I didn't really get what it's used for.
Yeah, so the create2 factory is basically just a contract that when you call it here, where is it? Let me check. Yeah, when you call save create2, all it does is it uses create2, and because if you look at how the create2 address is determined, the creator address dictates where the final the address of the final contract, right? So if the factory itself is deployed at different addresses on different chains, then you will get different contracts, even if the salt and the init code are the same. So this factory is like a contract that one person has invested a lot of effort into deploying on the same address everywhere, and then everybody else can very easily have the same factory on a bunch of different chains to make sure they get the same address. because the way the factory is deployed is with a normal wallet deployment. If you look at the transaction, it's just a wallet that directly deploys the factory, or not even.
Yeah, I wonder like
Wait a
why
minute.
they have sender address in Create 2. Like, why would you do that?
So because you want different contracts, like a bunch of different contracts could be using Create 2, right? And imagine two different contracts, both use the same salt and init hash. So you need some way to have a different address at the very end.
Okay, I see. But yeah, I mean that like Create 2, it's on the same address on Optimistic and BS like Binance Smart Chain and other chains as well. Yeah.
Mm-hmm.
I read about
exactly this factory.
Interesting hack, and I'm not sure if it's, but I guess it's possible. So you have a factory, and this factory creates some contract with normal creation, new contract something, and after that you destroy self-destruct the created contract. You also call self-destruct on the factory, and when after that you deploy again the factory, but the nonce is being reset to 0, and you can deploy new contract, the original one, on the same address but with different implementation. Did you understand what I mean?
Yeah. I see. Yeah, that's
To
actually an
reset
interesting
the
way.
nonce, idea is
So
to reset the nonce, but to use the normal create one.
yeah, that's a good point. Yeah, that's one way. That's one way you could do it. Yeah. That's actually really smart. Yeah. So basically, not sure if everybody got that, but basically, yeah, because the address for normal create deployment is based on the nonce, and self-destruct resets the nonce, right? So if you imagine you have a factory contract that deploys a bunch of contracts, and every time the nonce increases from 0 to 1, 1, 2, 3, 4, 5, etc., and then you destroy one of the contracts that was created from the factory, right? So let's say you destroy the contract that was created with nonce 3, and then you destroy the factory and redeploy it, resetting its nonce to 0, and then you recreate contracts. Now you can deploy a different contract
on the same
to
address.
that same address.
Yes, yeah.
So there's different ways to do this, either on purpose because you want to upgrade your contract and change its code, or maliciously because, like, for example, the Tornado governance hack where an attacker made a proposal that looked legitimate, but he had a function where he self-destructed the proposal contract and then replaced its code with something malicious that allowed him to steal funds. So this pattern can be used both maliciously and constructively because via the so-called metamorphic contract pattern. So usually normal proxies, as you reviewed them this week, they're usually like a delegate call contract that point to a certain address, and you just update the storage slot, right? So you update the address that it points to. That's how you upgrade. But that adds a lot of overhead, right? Because 1, you have to read the storage slot, and 2, you have a delegate call to a cold address. So that's at the very least, a proxy will always add 4,700 gas to every single call. Now, the advantage of a metamorphic contract is you can upgrade the code in place. That means you don't have to read a storage slot for the implementation, and you don't have to call a separate contract. So this can, just in gas savings alone, is already kind of cool, but it's going to be deprecated very soon because with the Cancun upgrade, they're going to deactivate self-destruct. So that's not going to be possible in the near future anymore. They're going to remove self-destruct.
Unless you use it in the constructor, right? Which I don't know what's the point, but yeah.
Yeah, exactly. But that still doesn't allow you to use the metamorphic contract pattern. But yeah, you're right. You will still be able to use self-destruct if you destroy as part of the same transaction.
So like.
But yeah. Otherwise, any questions in terms of determine?
If you deploy,
sorry,
if you have create 2, like you call it with the same salt and with the same contract, like 2 times in a row, it will, on the second time it will revert, right?
Yeah, exactly. Like the factory explicitly checks that you don't deploy twice, but even the create2 opcode itself, if you try to deploy to an existing address, it'll just return the 0 address on the stack.
So you have to like self-destruct that previously deployed contract, and then after that you can like redeploy.
Exactly. That's how metamorphic contracts typically work. So because you want to be able to you want to be able to self-destruct and then redeploy new bytecode. But on top of that, you have to make sure that the init bytecode stays the same, because the create2 address, if you look at the definition, it depends on the hash of the init code. Now, the init code is just a constructor, right? So it has to stay the same. But if you imagine a normal Solidity contract, the init code contains the entire runtime code, because that's how it works, right? The init code is like a small piece of bytecode that runs, and it copies itself and returns the runtime code. Now, this, if you want the metamorphic contract pattern, you cannot use this, because then if you change the code you want at a certain address, the init code, and therefore the address will also change. So the way this works is that you have a special contract which actually has the same constructor, but what it does in the constructor is it fetches with an external call the actual bytecode. Like this, the constructor always stays the same, but it can still return a different deploy byte, a different final bytecode, if that makes sense.
Yeah, that's interesting. Yeah.
I kind of also not for the metamorphic contract pattern, but for SSStore 3, this library I wrote, in my thread I kind of explain how this works, because it has to use a similar concept in terms of retrieving bytecode in its constructor, so that the init hash can stay the same, but you can still deploy different things. Let me find it. I also made a small diagram, so I think that would be nice to visualize. There we go. Okay. Let me share, if it'll let me. Okay. Can you guys see my screen?
Yeah.
So basically, the way it works is, so you have the main contract, right? You can imagine this like the factory, and then it does create2. So now it starts the constructor of the contract you're deploying. And now within that constructor, it'll actually call a function that gives it the actual bytecode that it'll return. So what this does is that the constructor and the hash of the constructor will stay the same, right, for the create2 and the final address. But the actual bytecode that gets deployed to the address is what the constructor returns. That's how the EVM works. So you have the return opcode in the constructor, and whatever stream of bytes it returns, that's the new runtime bytecode. So that can be different because it's retrieved from within the constructor and not actually part of the total bytecode. So that's how, you can keep the constructor the same, but the final runtime bytecode can still be different. And that's what you need for...
This is very, very interesting. I didn't know about it. I mean, very tricky, but helpful.
Yeah, and also as like developers and hackers, like it's good to immerse yourself with these different like things, even if they're edge cases and you more often than not won't need to think about this, but occasionally it can be an interesting threat vector or things that I go into. Although I was listening to a few podcasts recently in terms of like smart contract security and everything, and it does seem like security researchers often say that the majority of bugs are really the basic ones, like access control modifiers that are missing, lack of input validation, reentrancy. So, it is in general best to focus and specialize in that because those are the most common cases. But, if you want to be the best of the best, it's good to have a large overview and immerse yourself in like different edge cases and just like learn about different things. So I hope this was useful and you learned about how to deploy contracts, because actually often when I speak to other devs, they don't even know about this like circular pattern, or like how do you set up circular dependencies like this. So yeah, I think at least this part is something you will encounter relatively often, and knowing how to do this will save you and your applications a lot of gas and also a lot of complexity in terms of the deployment procedure. Although, I mean, to be fair, you can also argue that having to compute the address in advance makes it a little bit more complex than just having a setter. But I guess that's your perspective on things. Can argue both ways. Oh, any final questions?
Yeah, I have a question regarding like that deployment contract in Foundry. So is everything that in that in that contract, is it like executed in one transaction, or it's multiple separate transactions?
No, it's multiple separate transactions. So everything between the start and end broadcast will be real transactions, except for view functions. So if you call a view function, even between the start and stop broadcast, it will not trigger a real transaction. But anything that like actually has to modify the chain will be broadcast. Oh, actually, I didn't demonstrate that. I didn't demonstrate actually running the transaction.
It's tricky because like it seems like you're writing a contract in Foundry that like will get deployed, and then from there it will the run function will be executed, but it's actually not.
Yeah, it is a bit confusing to wrap your head around. So basically, yeah, the deployment script contract will not actually be deployed to the actual chain. So the way it works in the background is Foundry will deploy and run virtually and locally the deploy contract, and then communicate to the actual RPC every time you have like a transaction to send something out. All right, let me actually run it just as the last final thing to see how it looks like. So if we add broadcast, it'll actually create the transactions. You see now it also looks slightly differently than before. So now it showed me, okay, we have the first transaction in the hash with the contract to be deployed and the second one. And if you look at the chain, if we scroll down, you'll see that it actually created two transactions. So block one, this transaction, block two, another transaction. Everybody see that? Or is it lagging?
Yeah, I think that makes sense.
And you can also see here like how much gas you used, and it'll have like a fake gas price because it's all local, right? It's Anvil, so I can spin it up anytime I want. It also shows you here every RPC call. It'll show you what was called. So also quite useful. And actually, Foundry tests are not that good to measure gas consumption. So often when I do real benchmarks, I'll write a deployment script like this and then parse out the real gas use, because this includes the 21K base cost, and it also includes call data costs, which Foundry tests will not. So if you're doing gas comparisons or like want to do a real gas benchmark, this is also an important thing to note. But yeah, it was great chatting to you guys. And yeah, if you have any questions,
so
you're always in the Slack.
You're saying like you cannot use it will have an additional overhead in Foundry when you like measure gas?
No, it'll be missing overhead often. So for example, if within a test you call multiple like setter functions or something that interact with the same state, it'll only charge you the storage slot warming costs once. It won't include the intrinsic cost of 21,000. It won't include call data costs. So you don't get the full picture. You can still use it as a good comparison, and you can use the minus gas report flag to get like a nice table of the different functions that have been called and their average gas use, but it won't necessarily be representative of the real cost at the end. So that's a thing to keep in mind.
But for optimization, it's fine to use it because like that overhead doesn't matter.
Yes and no. It can be important, and there's like certain optimizations you can, and like certain overhead that is really important that it often won't include is like storage warming costs and also address warming costs, right? So if you call address for the first time in a transaction, it adds a cost. So those it won't include, and that's actually often quite important and also kind of overlooked.